Imagine the three-dimensional space all around you as a never-ending series of chaotic intersecting planes and crossing lines. To make sense of it, pick a single origin point and draw two arbitrary vectors, A and B. Together, they define a single flat two-dimensional plane. If you wanted to build a structure perfectly upright on this tilted floor, you would need to calculate a third vector that sits precisely at a 90-degree angle to the entire plane. This calculation is known as the cross product, or vector product. You will often see it presented as an intimidating wall of matrix algebra, but the math is not arbitrary. The cross product is a physical machine. To understand how it works, we have to build it from the ground up using pure geometry. This equation defines the physical length, or magnitude, of our new perpendicular vector. Because this length relies on the sine of the angle between our starting vectors, parallel lines create a mathematical dead end. If the angle is 0 degrees, the sine is 0, meaning no perpendicular cross product can physically exist. This diagram illustrates how to find the specific spatial direction of the cross product using the right-hand thumb rule. If you point your fingers along vector A and curl them toward vector B, your thumb extends straight up. But if you reverse that multiplication order, going from B to A, your hand has to flip upside down. Now the resulting vector points straight down through the floor. This mathematical note formalizes that physical flip. Vector A cross B equals negative vector B cross A, a property called anti-commutativity. Unlike normal numbers where 2 times 3 equals 3 times 2, multiplying vectors in 3D space is entirely dependent on the physical order of operations. We now have a new cross-product vector that maintains a strict 90-degree angle to both of the original input vectors simultaneously. Looking at the top of these equations, we can prove this orthogonality. If we take the dot product of our new cross product with either original vector, the result is absolute 0. This box shows how to isolate pure spatial direction from our calculation. By taking the cross product and dividing it by its own magnitude, we strip away the length entirely, leaving behind a pure unit normal vector called n hat. Reversing the initial vector order generates the negative counterpart, pointing exactly opposite. We now possess a mathematical tool capable of extracting a standardized, perfectly perpendicular direction from any flat plane in the universe. To apply this, we have to translate our arbitrary plane onto a rigid 3D grid. We do this by assigning standard basis vectors of length 1 to the x, y, and z axes, labeled I hat, j hat, and k hat. This section of the notes proves what happens when an axis interacts with itself. Because an axis is perfectly parallel to itself, crossing I hat with I hat yields a 0. This circular diagram acts as a shortcut for calculating the interactions between different axes without having to draw a 3D grid every time. Moving clockwise around the circle simulates the right-hand rule. Crossing I hat into j hat generates a positive k hat vector pointing upward. But moving counterclockwise breaks the natural cycle, mirroring a flipped hand. Crossing j hat into I hat generates a negative k hat vector. By mapping space this way, complex 3D directions can be perfectly encoded into a simple, repetitive loop of positive and negative interactions. To multiply two 3D vectors algebraically, we must apply the distributive property, multiplying every component of A by every component of B. This expansion produces 9 distinct spatial interactions. However, our rule for parallel vectors immediately streamlines the math. Since I cross I, j cross j, and k cross k all result in 0, we can strike 3 of those 9 terms from the calculation entirely. The remaining 6 terms are then sorted by their resulting directions. Each pair of components combines to determine the final magnitude along the I, j, or k axis. This 3x3 determinant matrix is the computational shortcut that organizes all of this algebra. We stack our basis vectors on top with the input components neatly in the rows below. By using a diagonal cross-multiplication method on this matrix, we reliably extract the exact spatial pairings needed for our calculation. This matrix method generates the exact same 6 grouped terms as our long-form distributive algebra, perfectly sorting out the positive and negative directions. These calculations explore the ultimate edge case, what the algebra dictates when the two input vectors are perfectly parallel. If their spatial components are strictly proportional, the cross-multiplication perfectly cancels out, mathematically guaranteeing a zero magnitude across the board. The determinant matrix functions as a perfectly organized filing cabinet for the right-hand rule and basis vector geometry. We've built the algebra, but we still need to answer one crucial question. What does the actual number generated by this matrix physically represent in the real world? Looking at this diagram alongside our original magnitude formula, we can evaluate our starting variables geometrically. If you visualize a parallelogram stretching between vector A and vector B, the term b sine theta actually calculates the precise vertical height, or altitude, of that shape. By multiplying that altitude by the base length of vector A, we calculate the exact area of the 2D parallelogram spanned by our vectors. Divided in half, it effortlessly yields the area of a connecting triangle between the two vector endpoints. The cross product links algebraic computation directly to spatial reality. It uses a matrix to simultaneously define a perpendicular dimension and quantify the physical area bounded by the input vectors.